Good morning, all of you. Today we will discuss on conservation laws for system of particles. First of all, we study about center of mass. Consider a system made up of n particles. A typical particle I has mass mi and at the instant considered occupies the position ri relative to a frame xyz. We can then define the center of mass G as the point whose position vector Rg is such that Rg is equals to 1 by m summation I is equals to 1 to n mi ri. Here m is the total mass of the system given by m is equals to summation I is equals to 1 to n mi. It is important to note that the center of mass is a property of the system and doesn't depend on the reference frame used. In particular, if we change the location of the origin O, Rg will change, but the absolute position of the point G within the system will not. Often it will be convenient to describe the motion of particle I as the motion of G plus the motion of I relative to G. To this end, we introduce the relative position vector Ri dash and write Ri is equals to Rg plus Ri dash. It follows immediately from the definition of the center of mass first and the definition of the relative vector Ri dash second. This and first is this. That means summation I is equals to 1 to n mi ri dash is equals to summation I is equals to 1 to n mi ri minus rg, means the value of ri dash is equals to, from here, ri minus rg, and put it here, is equals to summation I is equals to 1 to n mi ri minus mrg is equals to 0. This result will simplify our later analysis. Now, forces. In order to drive conservation laws for our system, we isolate it a little more carefully, identify what mass particles it contains and what forces act upon the individual particles. We will consider two types of forces acting on the particles. First is external and second is internal force. External forces arises outside the system. We will denote the resultant of all the external forces acting on the system as summation I is equals to 1 to n Fei is equals to F. Internal forces due to pairwise particle interaction, let Fij denote the force that particle J exerts on particle I, directed along the line joining the two particles I and J. This force could arise from gravitation, attraction, or from internal force due to the connections between particles. It could also arise from collisions between individual particles that, as we have seen, produce equal and opposite impulsive forces that conserve momentum. By Newton's third law, these internal forces act in pairwise equal and opposite direction. Therefore, Fij is equals to minus Fji, where Fji is the force that particle I exerts on particle J along the line joining the particles. The total internal force on particle I is becomes summation J is equals to 1 to n and J is not equals to I Fij. This will be the total internal force, and if we sum over all particles, we have summation I is equals to 1 to n and summation j is equals to 1 to n. J is not equals to I. Fij will be equals to 0. Since for every force Fij there is an equal and opposite force Fji for both normal and tangential forces, the notation J is not equals to I means to exclude J is equals to 1 in the sum, since of course the particle induces no net force upon itself. Now we study about conservation of linear momentum. The linear momentum system is defined as L is equals to summation I is equals to 1 to n mi vi. From equation second, means above, we have that vi is equals to ri dot, means differentiation of ri with respect to time, is equals to rg dot plus ri dot dash, which combined with the above equation gives L is equals to I is equals to 1 to L is equals to summation I is equals to 1 to n mi. Here we put the value of vi. Here we put the value of vi means rg dot plus ri dot dash bracket 1 is equals to summation I is equals to 1 to n mi vg plus dy dt summation I is equals to 1 to n mi ri dash is equals to m vg. Since by the definition of center of mass, summation I is equals to 1 to n mi ri dash is equals to 0, we now consider the time variation of the linear momentum. If we assume that the reference frame xyz is inertial, then starting from equation 4, we have L dot means differentiation of linear momentum is equals to summation I is equals to 1 to n mi ai, a means acceleration ai, is equals to summation I is equals to 1 to n fi plus summation j is equals to 1 to n, j is not equals to I fi j, is equals to summation I is equals to 1 fi is equals to f. This is equation 6, where F is the sum of all internal forces acting on the system. Since the sum of the internal forces balance when summed over I and J, we are left with only the summation over the external forces. Thus, for a system of particles, we have that L dot is equals to F. This will be equation 7. Now note that from equation 5 we can also write L dot is equals to mag. This is a powerful result. Note that the center of mass is in general not fixed to a particular particle but is a point in space about which the individual particles move. These ideas also describe the conservation of linear momentum under external and internal collisions, since individual internal collisions between particles in the system conserve momentum. The sum of their interactions also conserves momentum. If we consider an external particle imparting momentum to the system, it could be treated as an external impulse. Conversely, we can consider the particle about the collide to be a part of the system and include its momentum as part of total system momentum, which is then conserved by Newton's law. Now, conservation of angular momentum. Conservation of angular momentum. Since the angular momentum is defined with respect to a point in space, we will consider two cases using a different reference point for each case. First is conservation of angular momentum about a fixed point O, and second is conservation of angular momentum about the center of mass, which could be excreted in inertial space. The figure shows the system, the coordinate system xyz about the fixed point O, the coordinate system x dash y dash z dash about the center of mass g, the internal forces between particles, the angular momentum h naught about the point O, and the angular momentum hg about the center of mass point G, which is general are not equal. Now conserve angular momentum about a fixed point O. The angular momentum of a system of particles about a fixed point O is the sum of the angular momentum of individual particles. That means h naught is equals to summation I is equals to n ri cross mi vi. The time variation of h naught can be written as h naught dot is equals to summation I is equals to 1 to n ri dot cross mi vi plus summation I is equals to 1 to n ri cross mi vi dot is equals to 0 plus summation I is equals to 1 to n ri cross fi plus summation j is equals to 1 to n, j is not equals to I fi j close bracket is equals to summation I is equals to n ri cross fi plus summation I is equals to 1 to n mi, where we replace mvi naught by the sum of the forces acting on particle I. mvi dot is equals to fi plus summation j is equals to 1 to n and j is not equals to I dot fi j close bracket into summation I is equals to 1 to n mi is the sum of any external moments that act on the system. The term ri dot cross mivi, the term ri dot cross mivi in equation 9 is 0. Since ri dot is equals to vi, the two vectors are parallel and their cross product is 0. In the second term, we may write ri cross fij plus rj cross fji is equals to ri minus rj cross fij is equals to 0. Since the forces are aligned with ri minus rj and their values are equal and opposite, their cross product with ri minus rj is 0, and therefore the internal forces have no net effect on the total angular momentum change of the system. particle system. Therefore h naught dot h naught nahi sorry h at point O dot means differentiation of HO is equals to summation I is equals to 1 to n Ri cross Mi Vi dot is equals to summation I is equals to 1 to n Ri cross Fi plus summation I is equals to 1 to n Mi. When evaluating the moments which act to change the angular momentum from equation 13, we see that the sum of the internal moments is 0, so that the only moment which acts to change the angular momentum is the moments created by the external forces about the point O plus any external moments applied to the system. Thus we have HO naught is equals to MO, where MO is equals to summation I is equals to 1 to n Ri cross Fi plus summation I is equals to 1 to n Mi is the total moment about O due to the applied external forces plus any external moment. Okay, next time we discuss on conservation of angular momentum about G. Thank you for watching this video.